Okay, welcome to our demo about calorimetry and how we can take, we can add kinetic energy to something and change the temperature, and we're going to predict how much the temperature will change. We have a bag of lead shot there on the table, and we're taking track of its temperature. It is oscillating between 19.8 and 19.9 degrees Celsius. And we're going to add some kinetic energy to this thing by my trusty assistant here is going to lift that bag up to 2 meters high. You see we have our 2 meter stick there. She's going to drop that bag as quick as she can 10 times in a row from 2 meters, and then she's going to put that bag on the table. We're going to measure the temperature and watch the temperature rise. Okay, ready? We're going to count the number of times for her. Ready? Whenever you're ready. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Last one. Put it on the table, measure the temperature, put that rod in there so we can measure the temperature, and then we'll wait a little minute till the temperature stabilizes, and we have our new temperature is still going up a little bit. Okay, we'll take it as 20.9. 20.9 minus 19.8 is 1.2 degrees Celsius. That's our temperature change. Delta T is 1.2. Now, knowing the properties of lead, specifically the specific heat of lead, now we're at 1.3 degrees in temperature change, 1.3 degrees change. Let's go over and see why it should raise by that amount.
So we did our experiment. Let's actually show that we can actually calculate to within, 25–50% or so, how much the temperature rise should have been. So Q here is the amount of heat we added by dropping the lead 10 times. So we know it's 10 times the potential energy for one drop, right? So we have a factor of 10 for the number of times the potential energy, mgh. So the mass of the lead, in this case, the mass of the lead is, mass cancels out. So sorry. We're going to cancel mass on this side and this side. When we equate that to mc delta T, mass here will cancel mass here. So we solve for delta T. It's delta T equals this divided by the C for lead. Well, the specific heat for lead we can look up in a table in our book. Here's that specific heat. We dropped it from 2 meters, and G is 9.8 meters per second. We did it 10 times. That winds up being 1.5 degrees Celsius. And what was the difference we measured? 1.1 degrees Celsius. So that's a pretty good calculation. Now, our observed temperature rise is a tiny bit lower because, as you saw, as she was dropping it, little bits of lead was fluffing out. Did you see the little bits of lead dust fluffing out? So we lost some energy that way, just in some of the lead escaping the bag. And it took us a while to put the thermometer in and all that stuff. So we got pretty close. All right, so